It is predicted that oil will run out in 44 years and natural gas in 56 years, hence we must look to renewable resources. From 2008 to 2014, the amount of electricity generated by wind turbines in the UK increased from 1.5% to 9.3%. Wind energy is a rapidly growing industry, and as aeronautical engineers, we are excited to design our own wind turbine. The table shows our design constraints. We decided to design a turbine with 3 blades rather than 2, because a 2-bladed turbine needs to rotate at a faster angular velocity to attain its peak efficiency. This produces greater stress on the structure and a larger amount of noise pollution. For a given TSR, the power coefficient is higher for a 3-bladed turbine. Our objective in this project was to maximise the merit function, that is to achieve maximum power at the stated design TSR whilst keeping mass to a minimum.
Wind turbines need to be powerful, lightweight and simple. And the best way to achieve this is a trade-off between aerodynamic efficiency and structural rigidity. The key to understanding the aerodynamics of the wind turbine was to use a blade element. This approach divides the blades into a number of sections and measures the performance for each different blade. The oncoming wind vector and velocity due to rotation, as seen by the airfoil, are used to calculate the moment-producing and thrust-producing forces. The first of these acts in the direction of rotation and aids movement. The second tries to topple the motor. For every blade element, the vector diagram changes. The variation in loading along the blade leads to various types of blade failures. To avert these, taper and twist were used. Taper decreases the blade area towards the tip, so as to keep bending forces within the limit that can be withstood by the material. Twist is used to orient the airfoil in the direction of the relative wind, to reduce drag and increase moment-producing forces. Since our turbine does not use pitch control, as with modern turbines, we aimed at designing for optimal performance between 10 and 12 meters per second winds.
Following on from the theoretical background, let us consider the design process. The first step was to choose a tip speed ratio. Based on the knowledge that tip speed ratios for small wind turbines typically vary between 3 and 6, this was selected to be 4. Using this together with the Smith's optimizations, the chord lengths and twist angles of each blade element were calculated. The magnitudes of the forces acting on the blades were subsequently determined, and we could then proceed with the choice of airfoils. The airfoils were short listed from airfoil tools, basing the selection process on lift-to-drag ratios, large enough thickness to withstand the stresses, and operability in the estimated range of Reynolds standards for various wind speeds. Maximizing the component of lift in the direction of rotation increases the moment-producing force and thus the power. It can be shown that the power ultimately depends on the choice of airfoil, chord length, TSR, wind speed setting, and blade diameter, which was chosen to be as large as possible. Finally, aerodynamic simulations were performed using the wind turbine design software Coldplay. We carried out a stress analysis of the turbine and, in doing so, obtained an output for the optimum chord length distribution and twist angles.
The key idea behind the structural design was to create a structure that will be as light as possible as well as have an optimal aerodynamic performance. While making the structure lighter, we aimed to make sure that the critical stress in the ABS plastic was not reached at any point. We also made sure that by allowing certain stresses, we did not get excessive deflections, as they may have adversely affected the original design configuration of the blades and therefore impacted the performance of the turbine. So where do these stresses come from? Stresses in the blade arise primarily due to tangential and thrust forces that result from aerodynamic forces of lift and drag, and also from centrifugal force, which becomes very important at higher RPMs. Considering all of these forces, we analyzed the stresses on the blades on the basis of the engineer's theory of bending, whereby the blades were approximated as cantilever beams. During the stress analysis, certain assumptions and approximations were made. First of all, any axial deformations were assumed to be negligible. Secondly, shear stresses and torsion induced by aerodynamic forces and stresses due to gravitational forces from blades on weight were neglected. This approximate analysis is however valid for solid symmetric sections, and and is a reasonable assumption to make in our case.
To gain an understanding of how the force and moments act along the blades, both force and moments distribution were plotted. Based on the equations for tangential and thrust forces, the stresses were calculated by combining this information with moments of inertia obtained from the aerofoil data, such as thickness. The optimal coordinate distribution for the stress calculation was obtained from the Smith formula. This process was then systematically iterated with the aid of Coldplay simulations to find an optimal compromise between structural strength and aerodynamic emissions. The design of aluminium hull required a shape that would minimize the area, thus minimizing the weight. We used a shape similar to a nut. The corner of the shape helped avoid slippage with the cone and also distribute the stress evenly. Also, the symmetry of the shape allows for the grub screw to be included. And more importantly, keeps the center of mass aligned with the shaft axis, so as to ensure constant performance and minimize losses.
Processes involved in making the aluminium hull work: turning to reduce workpiece diameter and create the center hole, milling to produce the flat surfaces, drilling for the grub screw hole, broaching to make the keyway. Rapid prototyping was used to make the turbine parts from ABS plastic, and these were glued together. Due to printing limitations, the trailing edges had to be artificially thickened and later sanded to the correct shape. Modelling filler was applied to mask surface imperfection and ensure that the model was not deformed too much during sanding. The sanded model was then spray painted for a smoother, more attractive finish. Finally, to reduce inefficiencies related to out-of-plane wobbling due to misalignment of the turbine's centre of mass and the axis of rotation, we used the following technique to balance it. The turbine was repeatedly spun over a horizontal two-point contact wound to statistically determine the most common settling position. Correction weights were applied to improve mass distribution until the turbine showed no bias towards any position.
The wind turbine was tested in the Aeronautics department in the Donald Campbell wind tunnel. The objective was to test its self-start capabilities and performance at various wind speeds. The turbine was mounted on the shaft of the test rig in the center of the wind tunnel. The shaft was coupled to a torque transducer and a Hysteresis compressed air-cooled brake. The setup allowed for both controlled decelerations and accelerations of the turbine. Values of torque and RPM were then obtained by averaging the data. The maximum power produced at 12 meters per second wind was around 54 watts. The corresponding angular velocity was 2,319 RPM, and this was well below the 3,000 RPM limit. The maximum value for the power coefficient was 0.264, and the associated tip speed ratio was 5.06. The turbine performed remarkably well. However, the experimental power coefficient and tip speed ratio slightly differ from the design value. These variations largely arise due to differences between the Q-blade simulation and the actual experimental test. Q-blade does not take into account wind tunnel effects, such as solid blockage. Neither does it account for the surface roughness of the blades. Sanding inevitably distorts the design airfoil shapes. Additive manufacturing equally has limited precision. Variations in cooling rates and temperatures also affect the shape. During the test, both stall and resonance of the turbine blades were observed. Peaks in power output occur before the onset of stall. This leads us to conclude that maximum efficiency is achieved by operating at the edge of stall. Resonance was particularly visible between 4,000 and 4,500 RPM, and at around 2,200 RPM. During the test, it caused a noticeable increase in noise coming from the turbine. Noise pollution is a significant problem for wind turbines, and these resonant modes should ideally be avoided. Resonance causes instability of the power output and jeopardizes the structural integrity. The merit function could be significantly improved by reducing weight. This could be done by further reducing the hub's length, the thickness at the roots, and especially the cone size, as these were the regions with a lot of excessive material. Ideally, one should also anticipate the removal of 3D printed support material from the inside of the hollow cone, which adds weight and results in the turbine imbalance. The symmetries of mass were tackled by using correction weights. An improvement here would be to balance the turbine in all directions, not just the plane of rotation. Our turbine fulfilled the self-start requirement just under 10 meters per second breeze. By incorporating more twists in the design of the blades, self-start at lower wind speeds could be achieved. This would also allow more power to be generated at lower wind speeds.